Hi, welcome students to my second lecture on Green's function. Coming to the first slide, we start with a Sturm-Liouville operator L operating on a function y of x, and that will produce a function f of x. So the first equation is L y of x equal to f of x, which is a non-homogeneous equation because of the right hand side f of x. Now to solve this non-homogeneous equation, let us define the operator L into the Green's function x of t is equal to delta x minus t. Now if we define y as integral g of xt into f of t dt, now the equation 1, which is becomes, instead of y I'll put integral L of y of x, that means L into integral g of x f of g of xt f of x dt, which is also equal to L of integral g of xt f of t dt. But g into f of t is nothing but delta x minus t because of the definition of the Green's function. That means the Green's function into another function. If the Green's function into a function f will give you delta, Kronecker delta function, Dirac delta function. So as again we will say that integral delta Dirac delta function into f of t is equal to f of x. Therefore we will get again the first equation, that is if an operator operating on y of x will give you f of x. So we can say definition of the Green's function as it is an integral kernel that can be used to solve differential equation from a large number of families, including simpler examples such as ordinary differential equation with initial or boundary value conditions, as well as more difficult examples such as inhomogeneous partial differential equations with boundary conditions. Okay, this was already completed, and now as a brief introduction to the Green's function, let us apply this to a solution of a non-homogeneous partial differential equation like electrostatic field. Now I am having an electrostatic potential psi. So as we know that the non-homogeneous Poisson's equation is given by del square psi is equal to minus rho by epsilon 0. In the absence of electric charge, rho is equal to 0, del square psi is equal to 0. That means there is no source. If the source is there, it is del square psi is minus rho by epsilon 0. We know that the solution is 1 by 4 pi epsilon 0 sigma qi by ri. Coming to the next slide. As we know that the force between the two charges 1 by 4 pi epsilon 0 q1 q2 by r square into r cap, and again the potential is also given by the expression 1 by 4 pi epsilon 0 integral rho of r by r dr. These are the things which we are already studied in the lower classes. So at the point r1, the potential is given by 1 by 4 pi epsilon 0 rho of r2, where r2 is the position of the source rho, and the distance between r1 between the source and the point where calculating the potential is r1 minus r2. So we use psi as a potential corresponding to this system. Now let us come to the Green's function. Here you can see the operator of the Poisson's equation del square. So the operator L is del square. So L of G has to be Kronecker delta. So the L is del square. So del square G is minus delta R1 minus R2. Again we have a Green's theorem which we studied in other sections of the mathematical physics, where it is given by psi into del square G minus G into del square psi into d dot 2 is equal to, it is converting a volume integral to the surface integral psi into del G minus G into del psi into d sigma, where the right hand side is a surface integral which is bounding the volume given by the left hand side of the integral. So accordingly, suppose if we say that this right hand side becomes 0, the integral falls off faster than 1 by r square, we may simplify a problem by taking the volume so large, so the surface integral vanishes. So if the surface integral vanishes, we can say the both sides are equal. Psi into del square g d tau is equal to g into del square psi d tau. That means right hand side becomes 0. So the first that means the left hand side, the volume integral is equal to 0. That means psi into del square g is equal to g into del square psi. On substituting this in equations 1 and 7, we have substituting the value of del square g delta r1 minus r2 d tau 2 is equal to minus g into instead of this value, we are putting the value of rho by epsilon 0, rho of r2 by epsilon 0 into d tau. And by integration by employing the definition properties of the Dirac delta function, we will get, because we know delta of r1 minus r2 into psi of r2 is nothing but psi of r1. So that will become psi of r1 is equal to 1 by epsilon 0 integral g of r1 r2 rho of r2 d tau. So that is the expression. The expression 11 is what we got the expression for the potential at r1 due to the source at r2. So this is coming to the results. 1 del square of 1 by r d tau is integral is equal to 0 or 4 minus 4 pi if the volume does not include the origin, and minus 4 pi if the origin were included. So as we know here in this case, the Kronecker delta is equal to, the Dirac delta function r1 minus r2, Dirac delta function of r1 minus r2 is what we equal to the L into the Green's function. Accordingly, we will get the equation number 13. Suppose if we shift the charge from the origin to the position r2, that means r12 is equal to r1 minus r2. The Dirac delta function delta r1 minus r2 vanishes unless and until r1 equal to r2. This was already mentioned. The Green's function for the electrostatic case is given by g of r1 r2 is equal to 1 by 4 pi mod r1 minus r2. Accordingly, the solution of a differential equation, that is Poisson's equation, del square psi is equal to minus rho by epsilon 0 is equal to psi of r1 equal to 1 by 4 pi epsilon 0 integral rho of r2 by r1 minus r2 d tau 2. So actually the psi of r1 is a particular solution of Poisson's equation. We may add solutions of Laplace equation. One such solution could explain external field. So generally we can say L, that is an operator operating on a function y of at r1, that will give you minus f of r1, and the Green's function is taken to be a solution of L of g of r1 r2 is equal to minus delta r1 minus r2. Again, y of r1 is equal to integral g of r1 r2 f of r2 d tau. So we can say the solution, the particular solution at r1 of a problem is given by y of r1 is equal to integral g of r1. If I know the Green's function, I can find out the solution, particular solution at a value of a particular independent variable. So y of r1 is equal to integral g of r1 r2 f of r2 d tau 2. So for more understanding, please see this YouTube lecture. With this illustration of the Green's function, we will come to the end of this lecture.